Hello. Hi. Is my video visible? Am I audible? Hello.
Yes, ma'am, you are audible.
Okay, great. Yeah, thank you for that confirmation. So, good evening. So, welcome to today's tutorial session. So, it's 7 o'clock. I think I will start proceeding today because we have a small issue that there's a small power issue over here. So, we'll go ahead. I'm not waiting. So, I think, oh, this I need to switch off. Okay, no, all good. So, yeah, so let me share my screen. Yeah. Okay. So once again, good evening and welcome to today's tutorial session on urban utilities planning, water supply, sanitation, and drainage. As we have been discussing last week, so we started our sanitation system and like last week we did sanitation, so now here we are moving on to drainage systems also. How do you so it's a continuation basically, so the sewerage layout and water drainage planning. So this is what we discussed in week 8 in our video lectures, and so in lecture 36 and 37 we saw into 36 we saw into the water carriage systems. What are the pipings, how do you combine like mixed separate all these water carriage systems and different sewerage layout. Then in lecture 37 we saw into the how do we calculate the quantity of, or how do we look at the capacity of these sewer design, how do we design them, what are the calculations involved in that. And then in from lecture 38 to 40 we looked into stormwater drainage planning. So there we revisited some of the concepts which we already discussed during our initial lectures on rainwater. How do we calculate the catchment area, what is the rainwater which is collected in a region. So we again revisited those calculations in order to see how we can plan our drainage system, and under what circumstances will we plan a combined drainage system, or do we go for a separate drainage system. So all that we saw in detail. We also saw how IDF intensity, duration, frequency curves for uh, rainfall intensity can be plotted. So how do we predict what so there's a relationship between intensity of rainfall, duration, and the frequency in which a storm event happens. So all these we went into very much in detail during our in our lectures 38 and 240. So as always this week, today we will be discussing a few problems, some numericals, some questions related to the content which we discussed in week 8. So before we begin, this is something which you already know, but just to say, we'll be going into each question, and you can ask your doubts after the question, and we'll also have a final 5 to 10 minute discussion on any topic that we have covered till week 8. So yeah, so today we have a small power issue. So in case I'm getting stuck or any issue, please let me know. You can put it in the chat box, or you can speak out. Speaking out would be better because I would uh, get to know it better. So yes, so let's get started and let's move on to our first question. First question. One second. Yeah, first question. Okay, so match the following and mark the correct option for the correct match. So this is a very simple question which we have, I think this concept we have discussed in multiple lectures before also. So let's get started. So we have what different water carriage systems, combined system, separate system, and partially separate system, and their functions are given over here. So yeah, so I think Aishwarya, can you attempt this question?
Yeah, it's for A, it's 2
A
combined
is two.
system.
Combined system carries both sanitary sewage and storm water. Yes, correct. B. Yes, Aishwarya. Okay, so B is a separate system that they've asked. So we have two options. We have portion of stormwater which is allowed to enter the sewer carrying sewage, and the remaining amount flows in a separate set. So this is one possibility. Then there is another one which says the domestic and industrial sewage is carried in one set of sewers, and stormwater and sludge surface water in another set of sewers.
Separate system.
Sorry?
That is separate system.
Yeah, so this is
Domestic.
separate system, correct. Yeah, so separate system, you have complete separation. So here you have domestic and industrial sewage is carried in one set of sewage, which means all the sewage which is there, or the waste which is generated from industries or residences or domestic purposes, yeah, same thing, is carried in one set of sewers, and you have another set of pipeline which is laid to carry stormwater and sewage, which is the rainwater. By stormwater, we mainly talking about the rainwater which is collected. So yeah, so this is a separate system. So let's go into a bit more detail. Why is a separate system needed, or in which situations is a separate system preferred over a combined system, or what are the advantages of having a combined system? So in a combined system, you have both stormwater and sewage running through the same pipeline, which means your pipeline has to be a bit more bigger. Like, or let's say it's a size A, and you have both stormwater and sewage running through this. So in during the seasons where there is heavy rainfall, what happens is all the storm water will also come into this. So which means there is a possibility that you need to design this whole sewer to be of a higher capacity in order to cater to this storm water also. Whereas if you having a separate system where the storm water is carried separately, then it would be much easier to carry, because you're separating it out and you can carry the storm water out separately, because this is needed only when there is heavy rainfall. Whereas your sewage, the sewage line can be a more dedicated line. So you can have separate paths, you can completely separate it out. So it'll be useful. But in certain situations, when the rainfall is adequate enough and it's of like adequate quantity, in that case, a combined system is always preferred, because in order to clean the sewer, so the self-cleansing velocity of the sewer, which we discussed in our lecture, so which means it is a cleansing power of that sewer that will automatically come from the storm water. So because there is storm water in that, the sewage, there is always continuous movement. Or if the pipe is this big and your sewage quantity is not adequate enough, so there can be possibility where your sewage gets stuck in certain locations also. In that case, having a pumping a storm water also into this sewage system will help in cleaning this sewer line. So because of that, a combined sewage system is preferred. But as discussed, in cases when there's heavy rainfall, this can be a demerit also. It can lead to increase in like the overburdening of that sewage because of stormwater. Because of this, you'll have to design a larger pipeline, so which is not needed. So the solution to this is to go for a partially separate system where only a portion of the storm water is allowed to enter. So this in fact can be said to be like a combination of this both, where you have the sewage system and you also have a separate storm water line. And whenever you have, like, so you can channelize a portion of your storm water to go through this to get the self cleansing velocity, and to avoid such blockages or such accumulation of sewage inside the drainage pipe. And at the same time, you will not at the yeah, so at the same time, you will not be overburdening the pipe. So your partially separate system goes into option one, which says portion of the storm water is allowed to enter the sewer carrying sewage, and the remaining amount flows in a separate set of sewers. Okay, great. So that works out to option A. Any doubts in this question? Shall we proceed further? Okay, let's proceed further. So yeah, so this is what we discussed. So we have combined sewage separate. Yeah, so sewer usually it's gravity based, but we also saw pressurized sewer and vacuum sewer, which we will discuss again in some of the questions. So yes, so let's proceed. Question two. Sewage lines are installed in a vertical zigzag configuration in which of the following? A. Pressurized sewer system. B. Vacuum sewer system. C. Partially separate system. And D. Combined system. Yes. So Partha, do you want to attempt this question? No. Okay. So may I request Shivraj, can you attempt this question? Nobody wants to attempt. Okay. So any guesses, anything? What do you feel? Like where is the zigzag configuration preferred? Okay. So this is directly from our lecture. The
Vacuum sewers.
Okay, very good. Yeah, very good. So you're saying it's vacuum sewer? Yes, exactly. It is vacuum sewer. So, I mean, pressurized sewer is again, just to confuse you, like it's given over here, but it is in a vacuum sewer that we are using. Eventually, vacuum sewer also works under the principle of pressure. Like you're creating a high pressure. So the concept is that you have a vacuum, you have an box where all the residential sewage or from multiple sewer lines, it's getting collected over here, and then let's say this is the zigzag configuration that you have, and then you have your sewer STP over here. So in this place, so there is a valve where one sewage gets accumulated after that particular height, then this valve opens and then the sewage is sucked in. So this is a high, so from here it's a high pressure, so this is maintained at a high pressure, and then there's a low pressure which is maintained over here. So you know that when objects or anything moves from a high pressure region to a low pressure region, so when this valve opens suddenly because of the low pressure, this automatically goes inside. And now why a zigzag configuration is needed is the main concept, because in order to, so the pressure head is developed over here and the low pressure is developed in this end. So in order to maintain this pressure difference, the high pressure and the low pressure which is developed in this central region, you need a zigzag configuration. So we'll go into the details so you can understand that a bit better. So yeah, so this is the vacuum sewer system. It collects, yeah, so it collects sewers from different sources and conveys it to the STP. So this is what I was explaining. So you have your suction pipe and then you have your sewage pump. So the sewage pump is which, like, or over here you have a vacuum pump which creates that vacuum over here, or it creates that high pressure region. High pressure is created by creating that vacuum pump over here. So yeah, so you have a pneumatic pressure controlled vacuum valve which opens after a predetermined volume of sewage is attained in the sump. So that is what we were explaining, which I explained before. So you have a valve which opens when you're reaching that particular height. So why this is useful is that, so it collects the sewage in one particular location and then it opens only when it's required. Imagine it was constantly open, or this was not there and it was directly connected. So which means from our residential like WCs or from wherever the sewage is going, a high pressure will have to be created over there, right? So which means immediately there would be a suction effect, which is something which we do not want. So because of this, we use a sewage uh, pump and we have a separate space where it's collected. And then from there, it goes to this vacuum pump. So you see, this is the zigzag configuration which is there. So here is just explained that you have a zigzag configuration. And yeah, before that, we are saying that the difference in pressure between the valve pit, so valve pit, which is at atmospheric pressure, and the main vacuum valve, which is at high negative pressure, pulls the sewage and air. So now we'll see some more details, which was not there in the lecture. So this is some more addition. So if there is a slope, so it can take advantage of the slope, but it cannot. So it is to pull uphill or to through the natural slope it goes, but to pull something uphill, this vacuum savers cannot be used. We need like maximum up to 9 meters, maybe, like it can be, but more than that it's not possible. But this itself is a like a good value. Like 9 meters is a good, like you say, it's a three-story building, so approximately it's okay, but not more than that. And yeah, so this we have already discussed. Now this we have discussed. So finally we have the lines aligned in a sawtooth or a vertical zigzag configuration, so that the vacuum which is created in the central station is maintained throughout the network. So this is the most important point over here, that the zigzag configuration is the thing which maintains that vacuum. If we did not have a zigzag configuration, and if it was a straight line, then we cannot maintain that pressure difference which was there. It would immediately be lost. Now, because of the zigzag, because of the resistance which is created because of the zigzag configuration, that pressure is not like, there will obviously be some pressure loss when the valve is being opened, but that pressure loss is minimized because of the zigzag configuration. So if you're interested to learn more, like last class somebody was asking for some more reference material. So this one in CPHO upload in their website, there is an engineering manual which is given, and in that, in chapter 3, this has been detailedly given. So you can refer this link and you can access this, and if you want to read more, it would be useful. Okay. So any doubts in this question? No. Okay. So let's proceed further. Match the following sewage collection system pattern with its characteristics. So A, perpendicular pattern, B, interceptor pattern, radial pattern, and zone pattern. So the characteristics of the different patterns have been asked for. So yeah, so can we go who can, yeah. So how do we go? Perpendicular pattern, which of the which of the options are correct for perpendicular pattern? Is it the pattern adopted when the sewage is to be disposed of on land around town? Or is it sewers carrying stormwater are laid in such a way as to seek the shortest possible path to watercourse? Or is it option 3, sewers are connected to large size sewers that carry sewage to a common point where it's disposed with or without treatment? And 4, suitable for sloped areas. Yeah. So who can, yes, Aishwarya.
Its perpendicular pattern is to cover the shortest possible path.
Very good. Yes. Perpendicular pattern is to cover the shortest possible path. Yes. So what would interceptor pattern be?
Is to a common point.
Intercept.
The third option.
Sewers connected to a large sewer that carries sewage to a common. Very good. Yes, that is interceptor pattern. Now radial pattern.
Radial is to carry
First
what
one.
around the town.
Yeah,
To
radial
radial
pattern.
pattern.
This pattern is adopted when sewage
One.
is to be disposed around the town. Yes, very good. Zone pattern. So suitable for sloped areas. Yes, very good. So this one comes out to option, what is the option? A is right. Yeah, option A. 2 and 3. Yeah, option A. So let's see this in a bit more. Yeah, option A. So let's see this in a bit more detail. So this is what sorry. So we have the perpendicular pattern, which means it's the shortest. So the perpendicular, so we know that if you have any curve and if you take the perpendicular distance to a point, which means that is the shortest distance which is available from that point. So yeah, so that's why you have the radius, which is the perpendicular distance from the center to the outside of the circle. So yes, so this is the shortest distance which is there. So yes, so that is perpendicular pattern. Then you have interceptor pattern where you have the main sewer line. So the dark black one is the main sewer lines, and you have multiple small lines which comes from multiple regions, and then it connects to this main sewer line, and then it's disposed onto the nearby. So it can be treated, it may not be treated. So this also we saw what is the advantage of this, because in this case we can, like, if you in certain seasons where you don't want to dump it directly, or when there is a high tide where you don't want to dump, in that case you can channelize it out and then you can keep it, or you can keep it aside, or you can, if in case you want to do the treatment and then dump it onto the river. So before that you can channelize it and you can not directly throw. So whereas in perpendicular pattern that is not possible. It's direct through the shortest distance. It's directly connected to the outlet or wherever you are planning to dispose it of finally. And yes, then you have the radial pattern, which is radially outside. So anywhere, if you have multiple dumping pits around the region, then a radial pattern is good. So, and one of the advantages is that you can keep building on that. Like you have a radial pattern, you can, like, it's radially outside. So that point is there. So there are many. So it can be put outside the town or around the town. And then you have a fan pattern where so you have yeah. So this was not there in the option. So something which we missed was there was a fan pattern also where it narrows down. So you have something coming from here, it comes, and then finally it comes out over here. Yeah, so Then finally, you have the zone pattern where from different regions it's collected and it's going. So this is very simple. So I think there's no doubt in this. We can proceed on to the next question. So question 4, if there's any doubt, was it? No. Okay. Okay. So question 4, which of the following statements or statement is true concerning sewer design? Okay, is true, which means there's only one which is correct. Option A, lateral and submain sewers are usually designed for average flows of population. B, lateral sewers are designed for peak flows and submain sewers are designed for average flows of population. C, lateral sewers are designed for average flow and submain sewers are designed for peak flow of population. D, lateral and submain sewers are designed for peak flows of population. So we have lateral sewers and then we have what is it? Submain sewers. So, and then the question asks, which of this is designed for peak, or is it designed for peak or average? Is this designed for peak or average? Like it's that simple if you break it down. So yes, so let's go. Let's see that lateral sewers, are they designed for peak or average?
Peak flows.
Lateral is designed for peak flows. Okay, very good. So what about sub main sewers then?
It is also designed.
It is also designed for peak. Yeah, very good. So yes, so why? Because so you have your lateral or the main lateral sewer. Mainly, we're talking about the main sewer, and then you have sub sewers which are connected from this. So the idea why we design it for peak is that because we want the maximum quantity, whatever quantity. At no point should the sewer not be able to handle the load. Like at or to put it the other words, at all points the sewer should be able to carry whatever sewage is being generated. So that's why we always go with the peak demand. And if you're designing the main for peak demand, then obviously the latter should also be designed for peak demand because the from the latter is where you're getting it. So you're getting it, and if this is designed for average demand, then there is no need for designing the main for peak demand, right? So you get the peak from here, and then you get the peak in the lateral, the lateral sewers also, so that you can carry out the peak at all points. So last year when we had this live session, there was a huge discussion about this where some students felt that for laterals only average is required, but for peak we need to have, so for main, for sub-main sewers you need to have peak. So I mean, it's good that in this class it's come out nicely that both we need to design peak. So which one will their option be? Option D, lateral and sub-main sewers are designed for peak flows of the population. Any doubts in this question? No. Okay. Yes, we can proceed further. Yeah, so this is what we learned in our lectures also, that we learned this, that lateral and submain sewers are usually designed for peak flows of population. So question 5. Design infiltration value shall be limited to a maximum of dash percentage of design value of sewage flow.
Option B.
Option B. Okay, 10 percentage. Fine. Anybody else? Any other guesses? Okay, so yeah, so your Aishwarya is right. So we are there in this lecture. We have seen that we always need to take a design infiltration value because along while we are designing sewers, there can be certain water which is due to cracks or leaky joints, that there can always be infiltration. And if we do not calculate this infiltration value, then there would be a situation when the sewers are not capable to handle the sewage which is flowing through it. So that because of that, we need to calculate this. And this design infiltration value is limited to a maximum of 10% of design sewage flow. So this is a standard which we always follow. We always take a 10%. Or otherwise, if it's ground fault or infiltration, we have these like maximum and minimum value. Certain guides are also given. But safe side, this 10% rule is always followed while designing. Any doubts in this? Okay, so let's proceed further. Question 6. Which of the following does the peak factor of sewage flow depend upon? A. Population. B. Population density. C. Site topography. D. Water supply hours. Yes. Any guesses? Okay, let's go option by option. Is population, does
All,
pop
all the four.
Okay, you say all the four. Very good. Okay. So, yes. So, let's see. Population. Okay. There's a power cut here. Let's see. Fine. I mean, it's running on inverter right now, so let's see for how long. I think laptop battery is fine. Yeah, 46 minutes. Yeah, we have time, no problem. So, okay, sorry for that digressing. So, yes, population. So, which of the four? Yeah. So, population, it depends upon the peak factor of sewage flow. Yes, if you have more population, then you would need more sewage flow. So, it depends. Yes, population. Population density. Now, if population is affecting, will population density also affect? Yes, population density also affects, because if the population is densely like it's similar, it's actually a related term. It's just that so in density what happens is your area also comes into consideration. Now area also influences the peak factor, so from where it's coming. So or in sorry, I went to the next question. Yeah, so if you have yeah, so if you have a region where this is highly dense region, this is like not so dense region, but there are people. So your peak demand, like your submains or your the the laterals which are coming, the sewage flow will depend upon the population and the population density which is coming from that region. So yes, population density also. And then site topography, yes, obviously, because if it's a slope site, then your sewer line or the flow, whatever we are designing, will also depend on that. Or if it's a high, then you need to pump the sewage up, so you need to have additional factors to be considered. So when you're considering sewage flow, we need to consider that also. How is the flow? So site topography. Then water supply hours. Yes, so what that is what we saw in the previous one also. Water supply hours will also, because based on the water supply hours, the sewage generation will also be will be affected because of that. So yes, water supply hours also. So all the four options A, B, C, and D. So this is there in our lectures also. We have discussed this in detail. All the factors which influence sewage, peak factor of sewage flow, and all the four will influence. So yes, Aishwarya, you are right. So any doubts in this question? No. Okay. So let's proceed further. Question 7. Flow rate at night is dash percentage of the average flow rate. What is the variation of flow rate from day and night? So here again, we are talking about sewage flow. So there would be a variation. Like in the night, it won't be as much as the during the day. So what is that variation? Any guesses? Okay. So this is
50
what.
to 60.
Yes, Vaishaka?
Okay, I was saying B, 50 to 60.
Okay, okay. Yeah, so you're 60, so somewhere you're right. It is around 60, but at a higher, like it's 60 to 70, which is there, which you can see on the slide over here. Yeah. So this is what we saw, seasonal and daily variation. So we learned in the lecture. So there will obviously be a seasonal variation, because in different seasons the activities people do are different, and based on that the amount of sewage generated may also vary. So there's a seasonal variation, and along with that during the day also there's a diurnal variation also. During the day and during the night it's different. So this is what we saw, like flow rate at night is usually 60 to 70 percentage of the average flow rate. Now, if you're looking at seasonal maximum, we always see that in any season, the maximum flow rate would be 1.3 times the average flow rate. Monthly maximum will be 1.4 and daily maximum will be 1.8. So this 1.8 is somewhere similar. Does it ring any bells? 1.8, have you seen this figure somewhere else? Yes, no?
Yes,
Yes. Where?
like fire supply related.
Okay, yes,
I
fire
think,
supply we saw, but mainly water supply related. Yes, when we were
what is up?
calculating the water demand, I mean, I understood you said fire because that's involved in the process of calculating water
Yes,
demand. You're right. So there we saw when we are calculating water demand, we will take the 1.5 times the seasonal the monthly maximum to be the da daily maximum. So it's the same thing. So over here, daily maximum flow rate of sewage. So you say there's always a relationship. So whatever water you're getting, so people are using that water, right? So sewage is generated based on your water supply. So that's why there's always a relationship between your water demand and your water supply. So this, I mean, this was just to brushed up that memory, that figure, to remember that easily. So it's again 1.8 times. But these two are new figures. Seasonal maximum is 1.3 times and monthly maximum is 1.4 times. So now again, so in the previous question we saw what does peak flow depend upon. So we discussed population. So because of that, so we see over here when the population is up to 20,000, we take a peak factor of 3. Now when the population is increasing, the peak factor is reducing. Why is it so? When population is increasing, shouldn't peak factor increase? Any guesses why this is happening? You can say your I mean, it's briefly it was discussed during the lecture also. So any logical reasoning why when population is increasing, our peak factor is reducing? Okay, so why this is happening is because when you have a larger set of population, when you have more number of people, or when you're catering to a larger area, there are more chances that the demand and the deficient of each can be balanced out. So you don't. So for instance, you have a very concentrated small population, which means the peak coming from here, like at one particular time, you have the maximum coming. So that maximum, so the demand is always there. That demand will always be fixed. Imagine this is a larger area, so which is there, like there's more households. So which means from here maybe the maximum demand is coming, but here maybe they're using less at that particular point, and from here also they're using less. So which means here it's not the maximum, but it's probably the minimum which is coming, and here it is the minimum which is coming. So which means when there are more people involved, or when the capacity increases, or when the population increases, the demand and the excess or the usage, it balances out. So some place there's maximum demand, some place there is minimum demand. But when there is a concentrated population, this balancing effect is not there. So which means mostly, like if there's a high demand, it's a high demand. There is nothing to balance that out. So because of that, we always go for a higher peak factor when it comes to a more concentrated population, or lesser population, and a lesser peak factor for a spread out population. Now, this is suitable for area also. If their sewer is catering to a larger area, then also this peak factor again varies because based on this. Because again, the same reason, whatever is the maximum is coming from one is balanced out by the minimum consumption. Or sorry, in water supply also we do this. Here again, it's generation. So the maximum sewage generated in one region is balanced by the minimum sewage generated in another region, and they all are coming together in the same design that we are calculating. So that's why this is there. Okay, so any doubts in this question? No. So let's proceed further. So we have question 8. Which of the following method is involved in intensity, duration, frequency curve generation? So intensity, duration, frequency curve generation. So this is for stormwater drainage system. We have discussed this in our lecture. So any guesses which is this?
Bernard equation.
Very good. Yeah, it is Bernard equation. What are the other three used for? Time area method, unit hydrograph method, and rainfall runoff process simulation. Like these three are used for one particular thing. Okay, so let's see. So yeah, so this is what we saw in our rainfall intensity. So yes, so just to give you a brief outline, so we have the rainfall intensity, duration. So you have the rainfall intensity, duration, and frequency relationship. So the ideal method to do it would be to actually collect the intensity data, plot it for how much duration it was there, and at what frequency it's happening, or what is the frequency which is there. So to define frequency, we always talk about return period of a storm event. So this term, I think you can keep in mind, return period of a storm event. It might come up again in your, I think in the form of assignments or questions or other future also. For gate examinations, I've seen this question coming. What is the return period of a storm event? So yes, so this is the average recurrence interval between equal events, or exceeding a specified man. For instance, right now or on a particular month, there was a storm which had a particular intensity or duration, and after certain interval this is repeating again with the same intensity. So this frequency after which it's repeating is called the return period, or what is the period after which it's coming. So sometimes we fix this one frequency. Let we say that I want to know what is the 5 year, for every 5 years what has been the return period, or how much intensity rainfall has come for every 5 years. So sometimes in our graph we make those like, so it can be a 5 year return period, 10 year return period, 15-year return period. So sometimes we can keep this fixed. If that is fixed, then we look at what is the intensity and duration which was there. Sometimes we can keep the intensity fixed. So this intensity, how long or how much frequently has this been there, and what is the duration of this intensity which has been there. So this graph basically gives us an idea about, so it's one, we've discussed this in a lecture. So it's in one graph itself, we get the idea about all these different these three variables. So this is what we saw. Now that was IDF relationship, and we use Bernard equation. Now for this, we need to first estimate the runoff. So to estimate runoff, we always go for rational method, time area method, unit hydrograph method. So the other three options which were given were used to estimate the runoff. So yes, so that's it. Okay, I didn't put the slide on the intent. So it's a graph something like this. I'll just show you. So we might have the intensity over here, the duration over here, and then your return period would be something over here. Oh, sorry, like this. It's the other way. I drew it wrongly. It's the other way. Like for instance, when the intensity is higher, the duration is low. It has to be this way. When the intensity is higher, the duration is lower. When the duration is higher, the intensity is low. And for a 5 year return period, maybe the graph is something like this. And for a 10 year return period, the graph is a bit more. Like for instance, when a 10 year, obviously you're taking your interval as 10 years, so the intensity will increase. So it would be at a higher intensity. So, and for a 15 year, probably the graph is higher. So this graph is there in the lecture in the PPT. So yes, so any doubts in this question? No. Okay, so we'll proceed further. So yes, so before we go into this question, just a word. So in case I go off in this system, I log in from another system. So please hold on, do not log out. I log in from another system, and we'll continue. So question 9. What is the rainfall intensity for a storm of 15 minutes duration using empirical formula in the absence of rainfall records? So yes, so let's do this. So this is a calculation which we need to do. So it's given as 15 minutes. So the duration T, or the duration of storm, is given as 15 minutes. So which is a formula which we will use? Do you remember which formula we'll use? Okay, so we learned something like this. In order to find the intensity of rainfall, I is equal to 25.4 A by T plus B. Remember this formula? So where T is a duration of storm. So this is what is T. T is a duration of storm. And what is A and B? So A and B are different, are constants. So this again, we saw in the previous graph, we actually need to collect the intensity of rainfall. We need to see what frequency and then plot it. But this is a easier or empirical method. So when you don't have actual rainfall record, we can use this empirical formula where based on previous experience or based on previous rainfall data, we have simplified these parameters A and B so that we can use these constants and get a rough idea about how much the intensity will be. Again, these will not be the actual intensity, but this will give a rough idea about the intensity. So we have, so our formula goes that A is equal to 30 and B is equal to 10 if the duration of rainfall is okay, let's say it's between 5 to 20 minutes. And A is equal to 40 and B is equal to 20 if the duration is between 20 to 100 minutes. So this you need to keep in mind. I think this is where mostly we go wrong, because it's based on the duration that we need to see. So if the duration is less, and this 20 is what we usually consider. So if it is, and again, if it is equal to 20, again, we go with this formula. Like this is less than. If it is 20 or more than 20, we go with the second formula. So this is not there. This is there. Like equal to 20, we go with the second one. So why this is happening? So which we saw in the graph before, which I explained, based on the duration of the storm, the intensity will also vary. Like usually for higher intensity storms, it lasts for a short duration. This is something which we physically observe also. High intensity storms are usually for short durations. So yes, so in this case, we will go with it's 15 minutes, which means it's less than 20. So we will go with this. A is equal to 30 and B is equal to 10. So yes, so that is what is written over here. So let's go with that calculation. So I is equal to 25.4 into A. So A, which is 30, divided by duration, which is 15. So again, duration is in minutes itself, because we are using everything in minutes. So we need not convert over here. Plus 10, because B is equal to 10, plus B, so B is plus 10. Okay. So now, yes. So how much does this work out to?
Thirty point 48.
How much?
30.48.
45. Okay. Is anybody getting any different answer?
30.
30, 30. Okay, very good. Yeah, 30.48. Yes, very good. And the unit is always millimeter per hour. So unit is millimeter per hour. Yeah, 28 minutes is good enough for us, no problem. Okay, so yes, unit is this one. Yes. Any doubts in this question? No. Okay, so let's proceed. Okay. Which of the following factors affect stormwater volume? A. Topography. B. Evaporation. C. Percolation. D. Absorption. Yes. Okay, so let's go option by option. Does topography affect stormwater volume?
Yes.
Yes. Yes, it does, because you have a topographic site, your catchment area. So you say catchment area. So if this is the catchment area I'm taking, because of the natural slope or because of the topography which is there, the water in the catchment might increase. Or if it's a slope like this, and if you're looking at this catchment area, I mean, we won't do that. We would be looking at this region only. But basically, based on topography, there can be regions where water is concentrated and there can be regions where water is not there. So topography affects stormwater volume, and from there it goes on to the river. So what and if it's on a completely flat region, then there are chances that surface runoff or stormwater will not be much, because it will lie over here and probably it'll get evaporated. Whereas if it's a region where it's being collected, then that evaporation loss is also reduced. So yes, topography affects. Then we have evaporation. Yes, so we just spoke about evaporation. The rate of evaporation also depends. The stormwater volume depends upon the rate of evaporation also. Yes, percolation.
Yes. Yes.
Yes, percolation. So all this percolation, evaporation, absorption all come under the same umbrella, right? Because you have water falling, so some gets evaporated, some percolates down, and some is absorbed. So percolates down means it goes as into the aquifer as groundwater recharge. Some are absorbed, like there is absorption, so which is there in the soil on the surface, it's absorbed there itself. So all this influences. So based on the soil property or the surface treatment which is there on the surface, ground surface, based on that, all these three phenomena would happen, and this influences the stormwater volume. So yes, so all the three. So all the four, yeah, all the four influences. Any doubts in this particular question? No doubt. Okay. Yes, very good. So let's proceed. Yeah, so this is what we saw. So yeah, so there were two factors affecting the catchment area, and then we also had the losses. So yeah, so these are the losses: evaporation, percolation, and absorption are losses. These are factors affecting catchment area. Yes. Question 11. What is the partial area effect? Runoff coefficient into lesser catchment area into higher rainfall intensity is greater than runoff coefficient into full catchment area into lower rainfall intensity. Okay. So and option B says runoff coefficient. Okay, so I think this terms might be confusing. So let's say runoff coefficient C, which is a constant. So in all the terms, runoff coefficient C is there, so it's constant, let's say. Then you have area of catchment, and then you have intensity of rainfall. So this is our CIA formula in order to find the total runoff which is there, the normal formula. That it just talks about that CIA by 360 we learned in our like module 2, I suppose. So this is that. So it says that when the area is lower, so this is lower catchment area and higher Okay, lower catchment area and higher rainfall intensity. If that is the case, sorry, that is the case, then that runoff is greater than area being full catchment area. So let's say area is higher and intensity is lower. So this basically, this is what is asked. Is this greater? Is this less? Or is this equal? I think, yeah, runoff coefficient of less catchment area is less than or equal to runoff coefficient of greater full catchment area into low intensity rainfall, and runoff coefficient into less catchment area into higher rainfall intensity. So which means this into the or yeah, lower rainfall intensity. Yes, this one, lesser catchment. Okay, so there's another option also, lesser catchment area and higher. Oh no, same thing is less than. So less than equal to and equal to. Yes. So, yes, so this is the relationship which is asked. If this is the case, what will it be? Will it be equal to or greater than? Yes, so any guesses? How will it be? So,
Less catchment area with a high rainfall intensity will be greater.
very good, yes. So this we have learned. So this is called partial, yeah, again, that is what is asked in the question also, partial area effect. It says that if you have a less region and if the rainfall intensity is high, so again, the rainfall intensity is very high, there are chances that it can be higher than having a higher catchment area but low rainfall intensity, which means it's being scattered here and there. And also because the intensity is less, whatever whatever you're calculating that, or whatever runoff you're getting will be less, because here in a small region itself there's high amount of intensity which is falling. And now TC, by TC is a time of concentration, or the travel time which is needed. So which is the minimum time taken for water to travel from one point to another point. So here it said that a lower travel time. So because the area is small, the time taken to travel will also be lower. So that's why lower TC is also given. When the area is big, the time taken to travel will also be higher. So again, in this travel, there can be a lot of losses, which we discussed, like evaporation, absorption. So because of this loss also, there can be some amount of rainfall which is being lost. So overall put together, having a low area and high intensity rainfall can create a higher total stormwater volume than having a larger area than a low intensity. So, and this is called partial area effect. Any doubts in this question? No. Okay. So before we proceed on to this question, I think my laptop might die out soon. So I'll just log out from this. Give me 2 minutes and I'll log in from another system. So before that, let me just save the recording.